Good morning, dear students. Welcome to this session on moment distribution method. So, this session we will derive expressions for carryover factor, stiffness, and distribution factor. Okay. So, last sessions we have talked about all these definitions and the mathematical expressions. Now we will derive the quantities of them. Okay. Right. Let us take the same beam AB where one end is hinge, other end is fixed. And if we apply capital M at A, it will be rotated by theta at A. And anyhow, theta B is equal to 0 because no rotation is possible at B. Okay. So, free body diagram of this one. So, remove the fixed support. So you will see the reaction M dash, okay, which will be of clockwise in nature. So applied moment is clockwise, reaction is also clockwise. Okay, right. So if you can just see this one, the free body diagram, if you see, it is not full free body diagram, it is only partial. I am not removing the supports, you see. I'm not removing A. A is hinge is there, and I'm just removing the fixity, and where I want only moment to be shown. Okay, you actually, if you say fixed end, we'll have two reactions, right? One moment and one moment rotation and one vertical rotation, vertical reaction. Okay, so this is what is meant by fixed support. Okay. Because this is a beam, no horizontal reaction. Okay, so what we want is only the rotation part we are interested. And I'm not interested in this vertical reaction. That's why I shall not see this one. I shall not see this one. If you don't want to see, what do? You put a support there. You put a roller. Okay, so only vertical reaction from roller is possible. That's it. So I want to see M dash. I want to see the reaction. So I removed fixed support. I don't want to see vertical reaction. So I put a support there again. Okay. So that's how it is. So M and M dash. Now what you do, there are two moments on a simply supported beam. Now you see there is a simply supported beam, one end hinge and another end roller. So I have two moments applied at A capital M and at B M dash. So two moments. So I'll take one moment first, then another moment next, then I will add both. That is equal to this one. Okay. So this is what is called principle of superposition. Okay. So you have two loads on the beam. So I'll take one load at a time and then another load next. Okay. So successive application of loads. So they are simultaneously applied initially. So they are simultaneously applied. Okay. Means at a time, two moments at a time. Now I'm taking them successively, one after the other. Okay. So let us see that. So when M is applied, so you have two rotations now because here we have roller now. So rotation is possible. So theta A1, theta B1. So this is clockwise. This is anti-clockwise. Now if you apply M dash here, you see beam bends upwards. Okay. So theta B2, second case, theta A2. Okay. So here it is anti-clockwise. Here it is clockwise. Right. So remember these two diagrams. So they are very useful for your derivations. Okay. So what we have done, we have taken a beam, one end hinge, other end fixed, and capital M moment is applied. Applied moment is there at A. So we have drawn partial free body diagram where fixity is removed. Only rotation is allowed. Only rotation is allowed, so that you can see moment reaction. Okay, right. Now you see that end A, I have applied moment M and I have notated the rotations. Similarly, applied M dash and I have noted the rotations. Okay, now let us come to those values. What is theta A1 value? Theta A1 value. What is theta A1 value? So rotation of a simply supported beam, rotation value, theta value of a simply supported beam where moment is applied. What is the value? ML by 3 EI, near end rotation value. Far end, half of that value. So all these things we have done in case of slope deflection method. You please refer to that no, uh, topic, slope deflection method. You will find all these things, right? The same we are using now. Okay, because moment distribution is nothing new. Only we are introducing distribution procedure. That's all. Okay, so this ml by 3 ei at this end. This end ml by 6 ei. Okay, so theta a1 value and theta b1 value, you see ml by 6 ei. Right? Similarly, now moment is applied at b. So theta b2 value is, now m means m dash. So m dash l by 3 ei is at b because moment is at b. Now what this will become m dash l by 6 ei. What are these values? Rotation values, slope values, theta values. Okay. So if you apply m, how much is the angle of rotation at A? How much is angle of rotation at B? We are able to write those values directly. How you get these values is you have to refer to the topic slope deflection method, because all these values we have derived there. Why you get theta a value when m is applied, ml by TEI is derived, right? By conjugate beam method, I think, if you remember. Or else you can use any other method, area moment method, or no, double integration, anything. So these are the values. You see, at B it is m dash l by 3ei. At A it is m dash l by 6ei. Now if you see theta b is equal to 0, I'm using. Okay, theta b 0 I'm using. What is theta b now? This is equal to this plus this one. There are two values at b. Okay, so theta b from capital M, theta b from m dash. So theta b1 anti-clockwise, theta b2 clockwise. So take anything as positive. Theta b1 is taken as minus. So anti-clockwise is taken as minus. Clockwise is taken as positive. Okay. Right. So substitute theta b1 and theta b2 values. So what is theta b1? ml by 6 ei. That is anti-clockwise minus. So what is theta b2 value? M dash l by 3 ei is equal to 0. So if you simplify this one, m dash will be equal to m by 2. Means what? If you apply some 10 kilonewton meter at A, what is m dash? 5, half of the value. So half will be carried from A to B. That is what is called carry over moment. Okay, you are applying 10 there and 5 is carried here. Okay, half of the value is carried to the end. So what is carryover factor value? M dash by M is equal to, what is M dash? Substitute for M dash, it is M by 2. So M and M gets cancelled, okay, in place of this one. So we'll substitute this. So M and M gets cancelled, it is 1 by 2. So carryover factor is equal to 1 by 2. Okay, 0.5. Okay, so it's very simple. If you apply capital M at one end, if the far end is fixed, this is important. You have to be careful with this. If the far end is fixed, then only it is 1 by 2. Okay, if the far end is fixed, then only it is 1 by 2. Okay, right. So carryover factor, how much? This 1 by 2. What is carryover moment value? M by 2, half of the applied moment. Okay, how you get this one? It is just by drawing some partial free body diagram by showing M dash, that is reaction. Then apply principle of superposition. Then use this condition of theta b 0. You get this carryover factor value. Okay, right? Okay, we'll come back to the other values in the next session. Okay, right. Thank you.